Hello everyone, my name is Taisia. I decided to record this talk because the internet connection isn't stable, but I'm gonna participate in the conference, like if you have some questions. And for this conference I'm gonna talk about the analysis of stationary remaining service time in queuing systems. So we will observe on N-class multi-server system, and we will mainly focus on the remaining service time in the system. So now about the model description. We have customers of different classes. They follow Poisson input flow, and the service times they have general distribution. And since the remaining service time is our main focus here, we will just instantly define them as S and Si. So conditional and unconditional remaining service time. Unconditional, it means it does not depend on the class. Now it's not that hard to derive the expressions for the distribution, precisely tail distribution of our service times, both conditional and unconditional. As you can see, it's formulas 1 and 2 respectively. Now we will go to the limits and express the stationary busy probability of a server when it's occupied by a customer of a class I. And basically to study one of our required limits for our remaining service time, we actually need to find the following limit. It's formula 4. So as you can see, we have an additional condition here, and we have to take that into account. Now we will get closer to the theorem formulation, which is the main result. And so we're gonna prove that this limit, formula number 4, it's actually distributed as the overshoot in the renewal process, which is generated by the original service times. And we will also define here the traffic intensity as usual for the class I customer, and in total one. Define the limit, so the stationary remaining service time. And we have to note as well that when we say that system regenerates, we mean that the customer comes to the system and finds it empty. This is a regeneration cycle. And now the formulation of the main result of this research. This is a theorem. So assume that we have rho less than m. M is the number of the servers in our system. In that case, the system is stable, and the target distribution, the one we need to find, equals, as you can see, the expression in formula 5. So it's actually consistent with what we did before, but we used to write a tail distribution, and it's not a tail, so we just have like 1 minus tail. We will give now the outline of the proof, because the proof itself is quite long, and we will focus on some main things here. First of all, we fixed an arbitrary server, since we have a multi-server system, and we will consider a process, B. It is the busy process, basically all the time when the server was busy with the customer of the class I. What we do next is we modify our system a bit. We will take the busy periods, we'll join them together in one, and put them in the beginning of the regeneration cycle. And yeah, we do it within each regeneration cycle. And we can actually see that more clear on this illustration here. So as you can see, this is our original process. So we have random idle times, random busy times, and important to note, when we say idle here, we actually mean that it's not occupied by the customer of a class I. So in fact it's not really idle, but this is just the notation that we use. So yes, original service process, and then busy process, and the modified one. As you can see, the regeneration period is here, and all the busy periods are coupled together and put in the beginning of the process, and of course they follow by some idle time. What we do next is construct the new process, the renewal process, from the original service times, and we can also see it here on the same picture. As you can see, there is no regeneration period anymore, because we just took all the busy periods and coupled them together, and so it has no gaps and it has no idle time, so this is just a busy time. We will also denote the remaining renewal time in our new process. which has the following limit tail distribution. So it also comes by analogy with what we did before. Now we will discuss the connection between our processes. So first of all, modified process and the original one. The most important thing here is that the limit tail distribution appeared to be the same for both processes, as you can see in Formula 8, and this is actually intuitively clear because in both processes, busy periods and idle periods are actually the same because we didn't change them. And in that case, the limits of the tail distribution would mean it's fair to think that it's also going to be the same. And this is an advantage because now we can just study the modified process, which is more easy because it has no gaps. So we're going to focus on this process. Now about the modified process and the renewal one, and about its connection. Well, of course, the renewal process is also received by, again, joining all the busy periods together. And most important, since we didn't have the original regenerating period for the renewal process, but the busy period, it actually can be used at the regeneration period because we only have the busy time here. And the service times, the original service time, they can also be used as the regenerative periods. And also, if we take all our previous results and some calculations, we can obtain the expression for the limit that we needed to find for our remaining service time, and you can see it, it's Formula 9. The not that easy thing here is this busy probability, which is unknown so far, so we're gonna find it. To find it, we will use some knowledge from the regenerative theory, then the balance equation, and to balance equation we can actually apply the law of large numbers, and coupling all this, we can receive the formula that you can see. This is Formula 10. This is the explicit expression for the busy probability. And also, I can just mention that it's also intuitively clear that we can just express this probability as a fraction of time when the server was busy by the customer of a class I divided by the whole time. And now we can get the explicit form. Now the only thing we need to do is basically to substitute our obtained expression, this one, to our formula for the distribution, for the limit, for the tail distribution, and we can see the result of at Formula 11. So now we can say that we actually received this in explicit form, and the theorem is proved now. So now we will modify the system by adding the possibility of the unreliable servers. So server can fail, and basically the interruptions, it's poison process. So after the interruption, it's following the setup period, which can be also generally distributed. And we consider two different types of interruptions. The repeat and the resume mode. I'm not gonna talk much about this because we already actually considered this model before in some previous paper. And the main matrix here is the generalized service time, which consists of the original service times plus the setup time. So it's just getting longer. Now we will do some analogy with what we did before in the original system. We also defined this generalized service time. To do this, we need the original service time and the setup periods with the distribution H, which is, as we know, is a convolution, which is also pretty hard to find. And to make it easier, we will use the Laplace LTS transform for that. And yeah, like I said, by analogy with previous analysis, we will define the following limit, which is the stationary remaining generalized service time. So now the Laplace LTS transform the following formulas. So basically the first one, this is a Laplace LTS transform of the generalized service time. This one is for the original service time, and this one is for the setup period. And we do everything, each of this formula for a class I. Now we will show how to use the Laplace transform to find the moments of the distribution of our remaining generalized service time. So there are the formulas for Laplace transform for both of our mods, the resume mod and the repeat mod. And I can just note here that as you can see, the resume mod formula looks more simple, and from the other side, repeat formula, it can take a while to actually calculate this expression itself, and then the moments. It's pretty hard. So there is a density that we can define also from the renewal theory, and to find the moments of the generalized service times, we need to take the Laplace transform, then calculate the generalized service time, take the derivative of that, and calculate the derivative in the point 0. So basically we do it one time, we will receive first moment, we do it 2 times, we will receive second moment, and so on. This is quite a common thing to do. And of course, to get basically the end moment, we will then plus one moment, we will have to know the end moment, as shown as in Formula 16. And of course, we have to be sure that this moment actually exists. And now a few words about the future problems relating to that one. So we can actually calculate these moments in the explicit form, which is quite challenging because the expressions are quite big, and Laplace transform, it also can be different and hard for some specific distributions, but of course it's possible to do that, so we probably have to use some packages or libraries or something else for the, again, specific distributions to finally calculate these moments in the explicit forms. And so again, in conclusion, what we did, we studied a multi-server system and we focused mainly on the remaining service time, constructed a modified system by coupling all the busy periods together, constructed the renewal process, which consists of only busy periods, with no gaps, with no idle times. Then we calculated the distribution of the stationary remaining service time using both of these processes, modified and the renewal one. Then we introduced a modified system with unreliable servers. For that we derived the expressions for Laplace transform for the remaining generalized service time, and we showed how to calculate the moments of the generalized service time. Okay, so there are some references, and that was all. Thanks for your attention.